It now gives me pleasure to introduce Sarah Light. Sarah Light's doing an evaluation of almond shell mulch application to established alfalfa fields. And we know that almond shells can be a problem as far as a waste product when there are not enough dairy cows around to eat hulls and other kinds of byproducts. And so this is an opportunity to return carbon to the field. With that, I think in a regenerative sense, it's important, and we look forward to your presentation. Sarah Light.
Hi, good afternoon. Thank you, Tim. And our field day is Tuesday, April 1st. It's an afternoon field day, registration at 12:30 and program at 1, and we'd love for you to join us. We'll be showcasing the hedgerow, but also doing a lot of soil health assessments and soil health demos, so it'll be pretty fun. Okay, my talk today is a summary of a project evaluating the application of almond shell mulch to established alfalfa fields. I did this with my colleague Rachel Long, who's a retired farm advisor for many decades with UC Cooperative Extension. So this is a picture of what we did. Basically, we applied these shells. I want to draw your attention to the fact that the alfalfa is already in the field. It's on top of the crop, so it's a mulch on top of the stand, but also to the way that the material is really blowing around. It's really lightweight, and so that was a challenge with this mulch compared to some other things that we might apply. I'll talk about that a little bit more later, but that was the first lesson learned with this project. So just some quick background. We are not only trying to build organic matter and build our soil health, but also there's increased desire to recycle organic matter in the state through different regulatory bills. And so we were curious if established alfalfa fields could be a sink for almond shell products. The reason we thought that they might be is because alfalfa is a legume, so it fixes its own nitrogen and it's deeply rooted. Almond shells are a pretty high C to N ratio, and so putting that amount of carbon into the top of the soil we thought would be a risk for tie-up of nitrogen. But because the alfalfa is fixing its own nitrogen and when established, the roots go down quite deeply, we hoped that that would not be a penalty to the crop. However, we wanted to assess it in a research setting before we started to really recommend it to growers. So we were really looking at the stand productivity. The question is, how does the alfalfa do, and what other soil health benefits might we be able to accomplish as well by doing this treatment? And we were worried about doing it in a newly planted field because younger alfalfa stands under a year have more shallow roots. Those feeder roots are all kind of in that soil surface, and so they have a bigger risk of nitrogen tie-up with that high carbon material. And that's why we did an established alfalfa stand, not to mention the fact that once a field is more established, there's more resilience to driving it over with equipment, et cetera. So we thought it would just be able to kind of be a better opportunity. And here is how we set up the project. Okay, I can't pull the microphone, but we had 4 blocks with our treatments randomized. We had our control alongside the almond shells, and the grower we were working with was interested in gypsum as well. Gypsum can be a good soil conditioner and can help with flocculation of soil, especially if you have a highly sodic soil with a lot of sodium in it. It'll knock that sodium off the profile and allow your soil to kind of loosen up a little bit. And so we thought it would be an interesting comparison since it is pretty commonly used by many growers. And so we included that in our treatment plan. So these were our 3 treatments, and this is the plot plan that we had set up. We applied the treatments 2 years to the same plots both years. And so the same plots got almond shells the first year and then again in the second year. And we started with a 3-year-old stand. So in year 1, we applied them in early October. The shells were applied at 4 to 8 tons per acre and the gypsum at 2 tons per acre. Typically, we would have the rate a little bit tighter. The 4 to 8 is kind of a range, but there was a lot of learning with the application in terms of how much you can really get onto one area because the material is so lightweight, because it blows around. And so we were learning as we were going. In year 2, we applied a little bit later on November 18th, and we applied the shells at 12.5 tons per acre, so we were able to really standardize that, but at a much higher rate. And then the gypsum was about 3.5 tons an acre on the plots. This is what the field looked like right after the application. So the alfalfa is there growing well, but the shells are pretty visible. I hope this is visible in the back. You can kind of see them here, and I'd be glad to show pictures later if you want a closer up view. And this is in year 2, very defined shells here among the alfalfa. After 6 months, there was still a good amount of shell mulch present on top of the soil, although it was surprising how quickly they broke down. We expected that we would have seen more shells after a year of application, but after a year, you couldn't really see as many shells as we expected. Even though they are a high carbon and kind of a tough material, they did break down pretty quickly. So that was great to know. But this is a picture of what it looked like after 6 months of application in year 1. And then this is 5 years of application in year 2. So even after a heavy winter rains and some spring warmth, there was still a lot of material present there. But the grower did not comment to us about any disruption to their operations from having this material on the ground. So it really was pretty flat. It gets matted down pretty easily and maintains a good mulch coverage, adding that really good benefit that we look for with our mulches. This is the yield data. I went through my slides actually just a few minutes after lunch and increased the font size as much as possible, so I hope everyone in the back can see. But this is a graph of the alfalfa yield data. We took 2 cuttings a year. We did hand harvest these plots. And I'll draw your attention to the fact that the color scheme and treatment order on all the graphs is the same. It goes as follows. From left in red is the control, in the middle in green is almond shells, and then on the right in the gypsum is in blue. And so those colors are going to match up in all the graphs. If you're not able to read the bottom, you hopefully can see that in the back. So this is dry weight in pounds per acre, and there was a slightly lower trend with the almond shells in the middle at the first cutting, possibly due to spring tie-up of nitrogen in those feeder roots, but they were not statistically significant. This is the October data from the first year, and the yield line is really flat. So any reduction in yield for the alfalfa that we had in that first cutting was really minimal and was gone by the fall. So we were pretty excited by that. We're worried that the alfalfa yield would take a hit from the application of the shells, but there was no difference. This is the yield data from year 2. It was similar. The yield with the shells is slightly higher in the summer than here. That highest yield point is this green dot. This is in August of 2023, that second year. So the almond shells actually yielded better than the other treatments, but no yield data at any point in that trial was significantly statistically significant. So though there was a slight reduction in both years, after that first application, it really did even out later on in the season. This is a picture of my colleague Rachel Long with a quadrat in the field. We did hand harvest with meter by meter squared areas, and we also used the meter by meter squared areas to collect our soil cracking data, our percent cover weeds data, and others. And so this is how we did it. And it was really a beautiful field and a pretty fun trial to work on, actually. So we didn't see any differences in stand vigor for the alfalfa. We went through with a smaller quadrat and we counted the number of alfalfa plants that remained to make sure that the shells hadn't killed any of the plants or affected the stand count, and there was no difference. Unfortunately, they also did not suppress any weeds. We were hoping we'd get some benefit of weed control, but we didn't measure that either. These are the stand counts and really flat line here with these treatments. I'll say sometimes we as researchers hope that all our data is statistically significant, but when we're evaluating a new treatment that we don't know how is going to affect the stand, we hope for data like this. None of the alfalfa plants died. This is great news for growers who might want to apply it to their fields. Now we get into some of the fun stuff with soil health. We looked at soil cracking, and soil cracking, if you can see this picture here, this is one of the control plots. It's kind of a clay-heavy field in Yolo County, so it really cracks a lot when it's dry. And soil cracking can be a negative, can be detrimental to soil health. It means that you don't have great soil structure, and so a reduction in cracking is an improvement. Not only that, but because alfalfa stays in the ground year after year, when the soil cracks, it can really tear those crowns and affect the alfalfa plants. And so we were pleased because the almond shells significantly reduced soil cracking. We took this measurement on 4 dates throughout the project. We used a quadrat, and it's all qualitative data. So we walked through and with our mind's eye rated on a scale of 0 to 10 the level of cracking, the severity of the cracking. We have the same person collect that data at every point so that there's no bias by the person who's collecting it. What I see as an 8, Cindy might think is a 7, and so it can be skewed if the same person doesn't do it. In this graph, what we're looking at is from 0 to 10, 10 being the most severe cracking and 0 being the least severe, what those values are. And the control and the gypsum have very high cracking levels in this clay soil as compared to the almond shell in the middle in green, which has the lowest rating of cracking. And so even after 2 years of almond shell application, we saw pretty quick changes to the soil physical structure, which I was pleased about. Having done a lot of cover crop trials, I've rarely seen changes this fast. And so with this level of mulch application, you can quickly see improvements. We also measured soil compaction. We used a penetrometer that measures the pounds per square inch of force required to push the implement into the soil. And the cool thing about the implement that we have is it actually records the depth, and so you can see the compaction at the different depths of the soil. We did not have significant differences at all the depths of the soil, but we did have a significant reduction in compaction in the top 3 inches. Now, we applied the almond shells to the top as a mulch, and then because the alfalfa was growing there, they weren't disced in. So it made sense that we saw that improvement to soil compaction and soil structure just in that top area where the shells were coming into contact with the soil. In this graph, we're looking at, on the y-axis, the pounds per square inch or force required to push that in, and then on the x-axis are our treatments. And the almond shells did have a reduction in the amount of force required to get the implement in the top 3 inches. Bulk density and aggregate stability, which tend to take longer to change, were not affected after 2 years of the trial. But the change in compaction was quite quick. These are some of the results next of soil chemical properties that we looked at, starting with potassium in this graph. This is potassium in pounds per acre. Almond shell byproducts have about 30 pounds of potassium per ton, and in year 2 we were applying over 12 tons an acre, so that's quite a lot of potassium. We did sample in the top foot, and we did not see any statistically significant differences by treatment. However, the alfalfa plots did have higher potassium in the top foot. Those shells take time to decompose, and eventually that potassium can leach down into the root zone. So we anticipate that over time there would be more potassium available. The other thing I want to note here is that we did sample in the whole top foot, and I do speculate a little bit that if we had done sampling in the top 4 inches and then 4 to 8 inches and then 8 to 12, that we would have seen a significant increase in potassium in that top part, but that there was a dilution of the effect because we sampled in the entire foot. We tried to sample what would be more of a root zone sample, but I do think if we had kind of stratified that, we might have seen more significant differences in these values. We are planning to resample this field this spring to see if there's any longevity from the treatment that's carried over 2 years after the last application, so stay tuned for those results. Soil carbon and organic matter were also higher in the almond shell plots, but the differences were not statistically significant. And again, I think if we had maybe sampled in a more stratified way, we might have been able to measure that a little bit better. But in the top foot, we see on this graph on the left, this is carbon in pounds per acre. The almond shells in the middle do have the highest value of carbon, but when we did the statistics on it, there was no statistically significant difference. And the organic matter, in contrast, was a pretty flat line with a little bit of increase in the almond shell plots. Other fertility measurements like cation exchange capacity, total nitrogen, magnesium, calcium, and pH were not affected by the treatment. This is nitrogen, a really flat line. The almond shells are a pretty low nitrogen. They're a pretty high carbon material, so we weren't anticipating big changes in nitrogen. However, we did see differences in salinity. This is electrical conductivity electrical conductivity, which measures salt content. The salinity was higher in gypsum. That is one note about gypsum, is though it can be a soil conditioner, it still is a soluble salt like our other fertilizer amendments, and so it really should be used with caution and when needed. It can lead to increases in salinity like any salt we apply to our fields, and we saw that here in this trial where there was significant increase in salt content in the field, in the plots that had gypsum as compared to the almond shells and the control. We also collected water measurements. We looked at infiltration as well as saturated flow and water volume. These are 4 graphs that are showing the water infiltration data. Water infiltration is a measurement of the speed at which water moves in at the soil surface. Some data that I'll talk about later measures the rate of flow into the soil once it's already saturated. But this is the rate of flow into the soil at the surface. We take up to 4 inches to simulate a heavy rain event and try to understand how those dynamics might be impacted. And 4 inches is sort of the NRCS standard a lot for this, although some people only go to 2 inches. This is a picture of how we collect that data. You put a ring there, pour water in, and time how long it takes to infiltrate. You may have seen other data in the past, or other people talk about a double ring infiltrometer. It's a similar way to collect data, just a slightly different method. We collected this in December of 2023, and we went to, as I mentioned, 4 inches. These graphs on the top left is 1, this is 2 inches on the top right. The bottom left is 3 inches, and then this bottom right is the 4th inch. And these are time and minutes that it took for that amount of water to infiltrate. And so the lower the value, the faster the water's going into the soil. The green for the almond shells is faster for all 4 inches of water that we applied. However, it was only statistically significant at that 4th inch. I was pretty excited with this data because increases in infiltration is a pretty important soil function measurement when we're looking at changes in soil health, and the results can be quicker to realize. So I was pleased that with shell application, there was basically an immediate change in the way that water moved into the soil. Especially, in the past few years, we've had some really heavy rain events in the early fall. I think our first rain this year was like 5 inches in Colusa, so pretty exciting to see that there's some rapid movement of water in with this quick application. This is a picture of the machine that collects the saturated hydraulic conductivity. What that does is essentially saturate the soil and then see how fast water flow moves after the field is wet. On the right, these are moisture sensors that we put in at a 6-inch depth to see if there were any differences in water volume in the plots. We did not see any statistically significant differences with the saturated hydraulic conductivity or the rate of flow into wet soil. However, it was faster with the almond shells. So we had many results where the almond shells were doing better than the other treatments, but we weren't able to really differentiate with statistics, which is kind of our gold standard in research. But still, from a practical perspective, the rate that water moved in was fastest with the almond shell plots, which is pretty exciting after such a short period of time. And then when we look at the water volume, in red here is almond shells and the blue is the control. This is water content in cubic centimeters. And so And each indicator line is 1/2 centimeter. So they're really small amounts of volume, the small water increments on this graph. The water volume was slightly higher in the almond shell plots in the winter and then slightly lower in the summer. I attribute that slight reduction in the summer to the fact that the almond shell plots yielded slightly higher. Alfalfa is a crop that can yield proportional to water applied, and so when you have more alfalfa growing, it's taking more water out of the profile. So there was more water that moved into the soil because of that improvement in infiltration, because of that improvement in saturated hydraulic conductivity and water flow, water dynamics. So when we're getting heavy rain events, the almond shells are helping capture that water and move it into the soil, getting it down and reducing runoff. And then in the summer, the alfalfa is yielding a little bit better and using a little bit more water. So that's pretty exciting too. And to move quickly into my summary and conclusions, what we did find was that shell application to established alfalfa fields does not appear to have a negative impact on stand productivity. It didn't appear to have a hugely positive impact on stand productivity, but it did have a positive impact on some soil health metrics, such as soil cracking, compaction, and soil water properties were improved with almond shell applications after just 2 years, so quite quickly. This project was just an initial application. We did not quantify the optimum rate of application or what changes might be measurable with a higher or low rate. This was really a proof of concept that I'm interested in furthering in more longer-term trials. Alfalfa may provide a good opportunity to divert almond shells, and the shells can be free, although somebody told me earlier today that they had heard of the price of them going up, but we had ours donated and they had been often available free. But they should be ordered early because there are landscaping companies and other competition for it. Since the shells are not incorporated, we anticipate that any nitrogen tie-up would be slow and only in the soil surface, and we do not recommend incorporating those shells prior to planting due to the risk of nitrogen tie-up with that high carbon material. We do not recommend applying the shells to a first-year stand, which is mostly drawing nutrients from the feeder roots in the top of the soil. Some considerations with application are that the shells are bulky and lightweight, so that can be challenging to spread. The first day we went to spread them was really windy. We had to come back. So I know that that's something we deal with in farming a lot, the weather conditions, but just note these are particularly lightweight and bulky and can fly around. But the advantage is that they're a dry material. We had ours at 6.5% moisture, so you're not losing transportation costs to water weight, like with some compost materials that come in really wet, and then you're paying essentially to move some water on. So that's the nice thing, is that it's pretty dry material, but more than 1 truckload per field might be needed for good soil coverage. In terms of the cost of application, the freight and spreading costs are pretty high. The freight was $10 a ton within 50 miles, and the spreading is $15 a ton. So the cost might not be worth it if you're far away. This is really a practice for kind of that carbon cycling, organic matter cycling, and really for alfalfa fields that are really close to an almond orchard where those shells don't have to be moved very far away. I did ask the CDFA if this would count as an incentive program under their mulching, and they said yes, but the requirements are that you have to have 70% coverage and a 2-inch depth of mulch application, which we did not achieve even with our rates. And so I do think that is something that I'd like to look into a little bit more, is how much would you have to apply to get to that, so that you might be able to get it paid for through some of the incentive programs, because of the great opportunity to build soil health and that opportunity to recycle our nutrients and our materials in our local farming areas. So with that, I really want to thank the California Alfalfa and Forage Research Foundation that funded this trial for both years, as well as our grower collaborator, Chamberlain Farms Lopez Ag Service, who did all our hauling and spreading for free, and Tayu Guan and Claire Aiken, who work with me. And I'd be glad to send any project summaries or answer any questions over email. My email's on the slide, so thanks so much. Any questions for Sarah? Right here, Stephen.
we have a microphone for Stephen?
Thanks, Tim.
Did you monitor the soil temperature, and was that why there was less cracking?
That's a good question. You know what? I do have soil temperature data, but I didn't look at it before this talk, so I'm not sure. I will take a look after this question, but I don't know if there were differences in it. Have you seen differences in cracking with temperature on your farm or in your research?
I'm a researcher, not a farmer.
In your
so-
research? Have you seen it in your research?
I mean, in general, you'll see with any kind of soil cover that you'll have lower temperature.
But have you correlated that to cracking?
No,
Oh, okay.
I haven't done it myself directly.
Okay. That time for that question or no?
One more quick question. We could.
Did you look at any residues on the almonds that you used, like any fertilizers or pesticides that might have been concentrated on them, and if they had any relationship?
We did an assessment of the almond shells for nutrients, but not for residue. So no, we didn't. But I would, yeah, I'll just say no.
Sarah, thank you so much. Thank you for your research. Stephen, I have a number of soil thermometers, and I'd like to lend you one when you're in Southern California, because I was at Dale's Ranch one cool day down in Blythe. It was just 100 degrees, and I put a soil thermometer in his fallow field, and it was 125. So this August, when it's 125, would you check the soil temperature for me? So I wonder what it would be. Dale, have you ever looked at that? What the temperature is when it's 125 day? 100 and what? 130? Yeah, I've heard soil get much hotter, and that can't be good for the biology. Let us thank all of our speakers this morning for a wonderful day. Thank you very, very much.